Okay, so I'm going to give you a sense of group theory. I can't give it all to you. And I'm throwing in the word multiplication. Why? Because I know multiplication. Okay? Multiplication since third grade. Group multiplication theory that's found in the standard model and on the t-shirt. So I'm not even going to cover the entire subject, just what's needed for the t-shirt. And the basic theory was known so many years ago. You know there's an identity element. You know there are inverses. And you know there's associativity. This from those two equals those two times this, whatever. There is one new idea, and that is the idea of closure. That is, if A and B are in a group you have defined, then so is AB, the result. Okay? Group theory can get really hard quickly because they have lots of letters, they have lots of numbers, they have lots of relationships between all these letters and numbers, and if you're in grad school, you get really good at all those kinds of numbers and relationships and whatnot. All right. So the standard model actually uses three continuous multiplication groups. It's called U1, SU2, and SU3. Here's this example of how they mix numbers and letters together. That is the covariant derivative for the standard model. Do I know how to use this for any practical calculation? Not the slightest idea. Okay? It gets really scary pretty quickly when you start to work with that. But the important thing that we can take from this is that if you have a symmetry, then you have a conserved charge. And how many terms that are in each one of those determines how many charges you have. For this Y thing, that happens to be U1, there happens to be like one thing that can generate it, there happens to be one charge, it's called electric charge. For the weak force, there are three things. And there are three weak field charges, and that's what that one is. And for the strong force, there are 8. And so there are eight charges. Okay. So let me show you what the U1 group is all about. It's basically complex numbers with a normal 1. And so if you just write a circle in the complex plane, you got it. That's got a nice simple visual. Okay? It's got a normal equal to 1. And this is about electric charge conservation. And it's if that was a complex value function, thingy, whatever it was, you divide by its norm, and that's always going to be on that unit circle. Now, you said that's a complex number, but I'm dealing with quaternions. Quaternions are simply 3 complex numbers. They share the same real. They just, instead of pointing in one direction, they point in 3-dimensional space. But I really think of them as being very similar. But the group SU2 is actually called a unit quaternion. And so these basically, it's a unit sphere in space-time, is the way I think about it. And you actually need 3 numbers to generate this group. And if you go, but why is that? That's when you start to get into graduate school group theory about why it really is 3. It's not hard math. I think it's n squared minus 1. But they can talk about that for a while as the way. So, but then it's 3 charges are conserved: W plus, W minus, and Z. Okay, and then there's this group called electroweak. And that has 4 things, and it's U1 cross SU2. So I said, well, if I'm using quaternions, why don't I just multiply them together? And because a quaternion has 4 degrees of freedom, it seemed like a thoroughly reasonable thing to do. And while I think this is a reasonable thing to do, I haven't broached this subject with somebody who is a group theory professional, so who knows whether they would attack me violently or not for suggesting this to you. Actually, we'll probably get more violent about this one. Because then I also noticed that 4 plus 4 equals 8. Okay, I get very sophisticated in my math, and it turns out that the group SU3 has 8 generators to its Lie algebra, to a reformer. And so I thought, well, why not just use 2 of these? And the reason is group theory, because if that really represents SU2. U1 cross SU2, then you get the same thing out of it. It stays in the group. That's the whole point of group theory. So I didn't So I was actually stuck here for, I don't know, year and a half. I work on this time scale. It's like, I don't have to get this done in a week. I can wait a year. I can let something bother me, piss me off for a year. I got so quickly to U1, SU2, U1 cross SU2. It's like, how am I going to reach out and grab hold of SU3? Because if I don't, I want to make this clear. I knew that if I don't get to SU3, I don't have it. I've got 2/3 of the standard model, doesn't cut it. All right, so my realization was, oh, what if I put a conjugate there? Then it's formally, you would say, its multiplication table is different. And so it makes a different group. But that thing, because norms multiply together, they stay the same. That's got a normal 1. That's got a normal 1. Everybody got a normal 1 on the table. I clearly have 8 choices I can make. Put whatever the heck values you want. You take the norm of that sucker, it's going to be 1. I can guarantee it. And again, I have yet to see this in the literature, but it's almost comic, the results of this. Because if you look on a Wikipedia and they say, we're going to show you how to represent SU2, you really want to hide under a couch if you see the details. Because you're not going to be able to go home and remember it, There's a square root of 3 here, and the 2 is over here, and the minus is over here. Mine work out to be plus 1, plus I, plus j, and plus k, minus 1, minus I, minus j, minus k. I can remember that. Those are the 8 generators of my group, my way of representing this group. Okay, that's the way you would. It's closer to how people would formally say it. I'm not formally trained, so I'm probably not quite saying that right, but it's something pretty close to that. Okay, so the biggest positives, actually, and I consider this from a philosophical point of view, enormous. Okay, there is this. The group theory, standard model has been around since the 1960s. They say it involves these 3 groups. And the honest ones will tell you, we don't know 2 reasons. There are 2 things about this. Why it's limited to 3, and why it's these 3 in particular. This is one of the reasons that physicists don't crow about the standard model. They're a little bit embarrassed by its success. Okay? I feel like I can answer that. Both questions. And it's all about the symmetries of 1 in 4-dimensional spacetime. Because if this thing, if I put alpha over here, if alpha and beta happen to be equal to each other, that's what I get out. And so it's trying to think about this in a group multiplication way that leads to these symmetries being in this Lagrangian, being in this symmetries in this Lagrangian, means there's conservation of those charges in the Lagrangian, meaning there's going to be electricity, or weak field, strong field. Okay? So what are the weaknesses? Oh, the weaknesses are scary. That I haven't solved a single problem with this as a proposal somehow being connected to the weak force. I mean, and that's just huge. Okay? I have not solved a single thing. I don't even know how to approach a problem with a strong force. Okay? There will be people that just say this is far, far too simplistic. Okay? Because some of the most detailed and impressive calculations done in all of mathematical physics are done with the standard model, and how you think you're going to connect that to reality is like a dream sort of thing. But it's something I can work on, and so that's why I just wanted to make sure there were big warning signs here about that sort of thing. All right, good. So we have to deal with spin. We are going to try to be able to spot spin 1 and spin 2 in a Lagrange density at the high school student level. Okay? So, spin 1 particles, whatever that means, okay, have this property that like charges repel. And spin 2 properties have properties that like charges attract. So the first one is great for EM, the second one is great for gravity. I can't, in a simple way, explain why that's the case. I can point to the book, Feynman lecture on gravitation, that's where it was made, and I accept this. I'm not going to fight this one, sort of thing. They talk about doing calculations about scattering and, sort of thing. I didn't go through the details. I don't understand. But I accept it. And so both of those types of properties are required for a unified field theory. Okay? So we're going to use quantum mechanical angular momentum projection operators. No, we better not, because that's too advanced, that's too fancy. All this stuff, amazingly enough, can be done without the jargon. And the key is that book by Feynman. And I spent, I think, 3 months reading like about 8 pages. I don't read fast. It's that I'm trying to figure out what's going on at my kind of level. And I finally saw, or we saw on page 39, he's writing x plus or minus ix, x plus or minus iy. It's like, oh, that's complex multiplication. You just do that, and you end up with this xx minus yy plus or minus 2x, 2ixy, whatever. That was on page 39. And then I went back. You see why I had to spend so much time. Sorry to read backwards. Back on page 34, and basically he's doing x plus or minus yi, x minus plus yi. That's all he was doing in terms of the algebra. So that took a while to see. And so if I write this out using conjugate operators, something kind of funky happens. There's, I guess I hit different terms on the top one, and here I put them both on the same side. Seems like an odd little thing to do. But something really important. You see those zeros? Did I not have that slide? Or did I get confused? Yeah. Oh, yeah. Well, I didn't explain this important property. The zeros on the end. That's what's important. Okay? To make a spin projection operator without using words, all I want to do is get a zero at the end. Okay? Zero, I understand. Spin projection operators, I get scared. Okay, so if I look at just the imaginary parts of this thing, then I notice that I get, if I were to add those two together, they cancel. If I were to add these two together, they'd wipe each other out. Okay, that's how I'm going to get my zero. I know how to get to zero. Okay, and then this is a step that I'm even a little fuzzy about. He's thinking about these in terms of, well, these guys kind of add up together, and it ends up being like a 2 theta I. And this one's is like a 2 plus I. And of course, if you add those two, you multiply those together, right? You multiply those together, you'll wipe them out. So the spin 1 stuff is the top line, and I guess that's a really lousy color to choose. But that's spin 2 down there. That's how you do it with complex numbers. All right. And I like and thinking about this. Feynman was a magician, and he works out in the open. But he was multiplying 2 currents together. The currents, if you go closely through this section of the book, he's using 4 vectors everywhere. Well, you can't multiply 4 vectors together. Okay? You're not supposed to do that. But he does that. And when he now switches over to complex numbers, he's putting the jx term, he's treating that as a real number, and the jy is imaginary. And it's like, and why is it pointing in the z direction when he gets through? It's like, I think he's right. I think he's getting the right results, but my accountant kind of person is saying, I think he's cheating. No, wrong word. I think he's doing magic. Okay? He is a skilled magician. He's really amazing fellow. I think most people will probably agree. With quaternions, none of these things are real. They're all the imaginary components, okay? And I'm going to do the same thing with hypercomplex things. And I'm just going to crank it through, and I'm going to get all the same darn terms, you know, but they're going to be kind of where they should be, as it were. And these things end up at Z because those are the rules. There's no me guessing sort of thing. So what I'm hoping is that the spin 1 is going to be this J times A thing, and the spin 2 will be the hypercomplex product. And so like charges repel, which is nice for EM, which is about spin 1, which is about curl, and like charges attract, nice for gravity, that's spin 2, and that, I think, is a result of the symmetric curl. Yes, so that is, hopefully gives you a sense a little bit more about the issue of spin, which normally is pretty darn hard to approach. So now we go on to the final one, the final section of slides, yay! Okay, we're going to try and find a static solution for the static Gauss's field equations. Okay, so the standard derivatives that you do in the high school, they just assume you're dealing with a flat piece of paper. It's like, well, what if somebody rolled up that piece of paper? It's like, I wouldn't talk to them again. No, but the covariant derivatives can actually deal with curved space and curved space-time. But things get hard, okay? Let's not kid ourselves. I think that the standard model basically says, hey, if you want to curve your space-time, that's fine with me. Just tell me what you did. This is called fixing the metric. And I'll proceed. Same thing happens with string theory. It says, look, just tell me what your metric is, and I'll go ahead. Well, what general relativity says is, well, no, it's always a curve, and I can figure out, I can calculate in only very few cases how it's exactly curved. What I'm going to try and hope with my G field work is that I can do it both ways. I can do it either way. Okay. So the G field solution of flat spacetime, well, Laplacian sort of thing, that was unknown to the 17th century now. And I am just pointing this out because it's kind of fun, particularly for freshmen who are going to be told the wrong answer. And they get the math right, but the physics is not. You really need to put that one up there. And you say, well, every single problem that they're going to ever assign to me, they're going to take the derivative of that. That one's going to go away. Why are you bothering me? It's because we're showing respect for Maxwell in a certain way. What happened was, you know, everybody who made super huge contributions, they contributed to light and to gravity, right? Newton did that to contributions to gravity and to light. Einstein certainly did. And Maxwell only made a contribution to how light works. What was his problem? Okay? And his problem, what he realized was that if he thought about electricity, how electric fields work, and he thought about how magnetic fields work, and energy conservation would work, he couldn't make them be consistent as far as the signs are concerned. And we know there's a fringe element that says, oh, we got to throw in a minus mass, you know, whatever. They were actually talking about this thing that bothered Maxwell. And I highly recommend this URL for a kind of more detailed explanation of it. But Maxwell said, I could add a huge number up in front of it and make sure that's positive. I really want to do that. I just have absolutely no reason to do so. Okay? And it turns out that along comes Einstein. Then Minkowski says, here's a solution, and then they say the Taylor series is none other than that one, where effectively we're throwing a huge honking positive number. When I say huge honking, it's because if you calculate that for the Earth, what is it, 10 to the minus 10 or something like that? Anyway, whatever, why don't we say it's a super small number? It's a super small minus number. That's what bothered Maxwell. He didn't want to put a positive constant that was 10 orders of magnitude bigger in front of it. You should have. You would have been right. But, and that will spell it out for you. But I bet nobody's going to throw that one in because they all know we're going to take the derivative, and so it doesn't matter. It matters to make a consistent story between EM field theory and gravity field theory. Okay, so we're going to try to get to a GEM solution. Actually, no, I take that back. GEM is the word I use for the unified field equations, and this is really a G field solution in curved spacetime. Okay, so covariant derivatives, they involve the normal derivative. Oh, thank goodness. And they also have this Greek letter. That's the scary part. Okay, so that has things in it for group theory. It has things for dealing with curved spacetime. And what you can do is think about, what if my potential A was really boring? Like, you take the derivative, you get nothing out of it. Then it would all be about the connection. And my first field equation, that rho thing, would be basically be taking the divergence of this connection. Okay, and I've actually seen it taught in a book, in one of these gravity books. It's like, don't take the divergence of a connection because it doesn't transform like a tensor. Well, that's right. I mean, it's not wrong. But if you have a really boring potential, then it's an okay thing to do. So you just have to add an additional stipulation. So what is that gamma? Well, actually, there's not an answer. There's a whole field of study, many different areas of study about what you should use. And it is hard to understand. And I'm going to use Christoffel symbols of the second kind, because that's what Einstein used for general relativity. But what does that fancy bit of math say? Well, it's basically, if you've got a metric, you start taking derivatives of these. And there's ones that depend on space, there are ones that depend on time, there are ones that depend on off-diagonal elements. That's something I haven't gone into. But guess what? Lunchbox physicists makes things easy. So I'm going to work with static and diagonal, so I only have to worry about space-dependent derivatives. Those are the only ones that matter. Okay? And so, and I'm going to make it further easy. Am I a lazy man or what? Well, maybe not with this many slides. Okay, I'm going to use this exponential metric. And if I do that, then what happens is well, if you take a derivative of this thing with respect to space, you get that thing back, right? And you take the derivative of the exponent, so you got that. And it's another vital detail that this Christoffel symbol also multiplies this by the inverse of that component. Well, the inverse of an exponential times the exponential, that wipes it out. It goes away. Okay. And so you go, oh, then I just want, oh, that's familiar. That should be familiar. The derivative of what is that? The Laplacian operator of charge over R. Okay, so the thing is that this exponential metric does not solve the Einstein field equations. And so I am in conflict with general relativity. I'm saying it's the classic way you talk about this, about in the science world. It's like general relativity is a wonderful theory. It has had a very long and productive life, and I got something better. That's my hope. How close am I to general relativity? Okay, what you do is you take a solution of general relativity known as the Schwarzschild solution, and then you do a Taylor series expansion, and then you compare the terms. And here again, you can't see any of those terms in green, but that's okay because they're the same. Okay, there's not any bit of difference in the green terms between what I'm proposing and what's there for the Schwarzschild. The thing is that when they say we've tested general relativity in the weak field, they mean they've tested exactly those 5 terms and no others. Okay? So if those 5 terms are the same, we are totally in agreement. We only get into disagreement when we get into these yellow things. Okay? And so who's right? Well, we haven't gone there. So I would, the reason I bet on my stuff is I'm more familiar with it. Okay. But being more symmetric is a better thing. My proposal is more symmetric. Exponentials, I like to say, are the calling card of a correct theory. It's like anytime you get really deep into stuff, they start sprouting. And why do they sprout like that? A good reason. It's because they, basically, when the exponential is super small, you get unity. Nothing happens. When your effect is super small, you better make sure nothing happens. Exponentials are good. Now, when you start something happening, you get some kind of oscillations going on, vibrations going on. That's what exponentials do. When you think about the sun going around the Earth, that doesn't happen. Earth goes around the sun. It's done this, what, 4 billion times? Now, is this, if I did this 4 billion times, would you say this looks like a simple harmonic oscillator? You know, I won't do that. But it's got that sense of, this is an exponential at work, okay? And my proposal actually predicts 15% more bending than it does than general relativity. And so why haven't they done this? Okay, because we know they did the experiment back in, what is it, 1919, and they had to fudge the data a little bit, you know, but subsequent tests, they showed that, yeah, Newton said it was supposed to do this much, what was it, 0.75 arc seconds, and Newton said it was, sorry, Einstein said it was twice that. And it was confirmed, it's rock solid. So now we just have to get to the next level. How many spots over do you have to go? Okay, this is obscure knowledge, I know. You have to go over 1,000,000-fold to get to those other terms. We've gone over 10,000, which is good, okay? We really are rock solid saying those first 5 terms, they're the same. It would take, you know, hundreds of millions of dollars and dedicated folks to go after those final terms, and then they're only 15% different. And then people can say, well, you know, there's a quadrupole moment in the sun, and that would be about the same size as your effect. So, so it's good on a philosophical level that they're different. It's frustrating that it's so subtle that I don't think I'm going to hear about the experiments done anytime soon. So here's the final slide. This is a comic strip provided by Lowell, who's a grad student in South. No. All right. Anyway, it goes, "What is this?" And on the chalkboard apparently is the back of the T-shirt. It's a new unified field theory I'm working on that disses the need for the Higgs boson. Looks like a real gem. Thanks. Doug misspelled forward his dog. And he's basically doing a riff on me because I talked about Doug being misspelled backwards as God. But, said, well, you know, when you misspell your name bad enough, you can really spell anything. So, yeah, that's a deep insight. So anyway, that concludes day 1 on deriving the Maxwell equations and more.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
I always wanted to do a lecture hall with a microphone like this, you know? All right, so seriously, so what does it take to do creative physics? And I think it's pretty clear. You really have to have a flexible mind. You really have to challenge who you are to yourself. Okay? And you can challenge, who you are, like in the kitchen. You can check out, in social situations. I better not go there. Okay? But you know what I mean. And I think you also need to be like really flexible in like a physical kind of way. Okay? How flexible are you? Okay, so I'm going to really challenge myself. I'm going to try and take my foot and see if I can put it behind my head. Because if I could do that, okay, I'd be a really flexible guy, right? And I could have, what I need to do theoretical physics. Okay, so I actually am going to have to remove my hand. Can I even touch my feet? Okay, there. I'm pretty sure that Hawking can't do this, okay? Was that cool? I'm not sure. Okay. I wasn't able to keep there a long time, but thank you very much.